All right, everybody, welcome to the second episode of RoboPapers. Super glad to have with us here Mahi Shafiullah, I think from New York University, to talk through his paper RUM. So let's rumble. Robot utility models, right? Anyway, Mahi, do you mind sharing about yourself?
Yeah, I can go first. I'm a fifth year PhD student right now at NYU. I work with Laurel Pinto. I'm his first student, actually. So it's really been fun 5 years, I would say, trying to work on a lot of different projects, a lot of different aspects. But my focus primarily has been working on robots and robot models that just out of the box works pretty much everywhere. That's what I've tried to focus on. And that's the continuation of that line of work is what has really culminated into robot utility models. Yeah, we call it utility models because at a high level, this is just, these are single task models. The goal is to provide some sort of utility for robots. And the hope is that if you have the right robot setup, which is pretty cheap to get, you can just download one of our models and start rolling it out on your own environment without having to fine-tune it or having to train it on some of your own data just out of the box.
All right, cool.
I should say I actually tested these.
Yeah, sorry, Chris.
They do. Oh, I should say I actually tested these. They do work. They did work at my house a little bit. They did. Yeah. So this was a unique experience being able to download and try it. Sorry, that was. Go ahead.
I was just going to say that when Chris even tried it out, it was with a different camera altogether, the wrist camera that we generally use for our robots, our iPhones. And Chris was using it with the RealSense camera, and we were not really certain if it's going to work out, but it worked out. So
interesting.
So I was too stubborn about it. I don't know an iPhone. So let's go ahead.
Cool. Yeah. I saw the paper. I got a bunch of questions. Yeah. That's one of them actually between when you guys switch between the iPhone and then RealSense and some other wrist camera. But yeah, maybe if you can share screen, maybe you can just dive straight in. If you can just give a overview once you share screen.
Yeah,
then we can just go.
Yeah, I can try to do that. Let me see. So I'll try to go over the very high level overview of the paper and then maybe go into a little bit more of the detail.
Okay, cool.
You guys can share. See the screen well?
Yeah. Okay, cool.
Yep. All right. So this is really the webpage for our robot utility model work. Again, this was a collaboration between us people here at NYU. There were some people who were at Meta, and there were some people who were helping us out from Hello Robot. That's the robot that we're using over here, as you can see. And we all collaborated together to bring this project into reality. This was a project that kind of continued on from a previous project that we had that we called Dobby. The paper is called On Bringing Robot Home. And on that paper, what we had a system that was built out of a few components. One of the big component is really like a handheld data collection tool we built with an iPhone. And the idea there was that once you have this tool, you can take this tool, for example, in your own environment, you collect 5 minutes of data and you fine-tune a pre-trained model for 15 minutes. And then your robot in your own environment should be able to do that one task that you just taught it to do. Now, this is an interesting prospect, right? Imagine you want to open a drawer in your kitchen and now you can just show it 5 minutes of data, 15 minutes of fine-tuning, then the robot knows how to open that drawer. However, one of the questions that we wanted to answer after getting to that point is how could you get a robot that can just open drawers wherever it goes? And you can intuitively think about it in this way, where I have this robot, I show it how to open a new drawer, takes 5 minutes of data, great. But how many times do you have to really show this robot how to open the drawer? How many times how to open the drawer before it just knows how to open the drawers anywhere? And that's what the question we're trying to answer here.
Just to clarify, when you say 5 minutes of collecting, are you collecting data, this 5-minute demonstration data on the same drawer that you're asking the robot to open, or completely different?
This was a previous project. Let me actually screen share the previous project, and then I think you'll get a good sense of what I'm talking about. So here is our previous project that we worked on. We called it Dobby. And this project was from 2023. For example, here is my own house on the left, and I'm teaching the robot how to put a rag into the washing machine. And so to teach the robot how to do this, you'd have to collect 5 minutes of data in that exact same environment. And this was our 2023 project. But when we continued on, the project that we did afterwards, the robot utility model, that was there to really get to a zero shot ability. Now you can just take your model, take your robot, put it in a new environment, and it should just work out of the box. That's the hope completely. For robot.
Yeah, I mean, the drawers comes in all kinds of shapes and sizes, different colors, different lighting, maybe different force that is needed. And somehow what you're suggesting is that 5 minutes of demonstration of opening some kind of drawers, literally you can open a different drawer somewhere else.
So this is
one other thing to note,
not
though,
exactly right.
It's just the video, the video, if you can see the video that Mahi was just showing, he mentioned that it was the Hello Robot. That was not the Hello Robot. That was a white, it looked like a KUKA.
That was the XR.
So
yes,
yeah,
this is the
So we also have
this is the
cross embodiment into your somewhere. Yeah. Okay. Just another dimension that I guess we got to.
Yes.
Back to Michael.
So just to go back to what Michael was mentioning before, right? We were talking about different environments. And so here on this project, we actually take a lot of those snippets, right? A lot of those 5 minutes of data, we pull it together from a lot of different environments, and then we train one big drawer opening model on all of that data. So what we do here is actually we take 25 demonstrations from around 40 different environments. So you get around 1,000 total demonstrations. And collecting around 25 demonstrations, it takes us about 5 minutes, right? So you can think about like 5 minutes of labor at 40 different environments. When you pull it all together, when you train a model on top of it, what you get is a model. Then you can just take it, put it in a new environment on a drawer that it has not seen before, like what you're seeing here, and it should just be able to attempt to solve it. That's the idea. So here we're going beyond that 5 minutes of data and pulling a large amount of drawer opening data and trying to see, can we train a model to do that? And it's not just about, let's say, drawer opening particularly. It is about getting to the point where we have a general recipe. Imagine you have a task that you care about. How do you collect the data? How do you model the whole task so that you can get a model that works in new environment zero shot? That is really our goal in this project, if that makes sense.
So we have 1,000 demos per task for 40 environments. So you said that was like 45 minutes of data total. Is that right?
5 minutes times 40, so 200 minutes, I would say.
Okay, so we've got 3 hours of data total. That's pretty good if it can really work anywhere. So how did you decide what the tasks were that you wanted to cover?
I think so here's kind of like the 5 demo tasks that we worked on when we were working on it, right? And I think we wanted to get some level of functionality. So we've always cared about, like opening, for example, doors and drawers, because our lab cares a lot about, for example, getting robots into homes. And doors and drawers are probably the most commonly seen articulated objects that you'll see and you'll interact with over the time of the day. And then once we had kind of a general recipe, we wanted to validate it and see if it works on other kind of tasks. So that's when we went into this reorientation type of tasks, right? Reorientation here is basically you take a bottle, right? Imagine this bottle. It's just lying on a table. You pick it up and you put it upright. That's the reorientation task. And then we did a couple of other tasks, bag pickup and tissue pickup, just to validate the kind of inferences that we're making from data. Try to get a sense of like the recipe that we have for data, does it actually generalize to new tasks? And so that's kind of how we ended up with the 5 tasks that we're showing here. However, I really want to emphasize that it is not about solving these particular 5 tasks. This is about understanding, if you care about a new task, how should you go about it?
Were there any tasks maybe that you tried that didn't work?
That's a good question. So from the previous project, right, like from the Dobby project, we had a pretty good sense of what is the limitation of, for example, our robots, right? So for example, we know that like it cannot deal with some very heavy object very high up. We knew, for example, that it only has a limit of the pitch between positive 90 and negative 90 degrees of angle, right? So there are some tasks that we thought about and then we just didn't do it because we were afraid that like, the current embodiment probably would not work out. But I would say that is probably, yes, that's probably a question of like getting to the right robot setup rather than like a limitation of the policy or the method itself.
So it's 100% hit rate, but you think that's mostly because you had a good intuition for what would work.
Exactly. I think once we have like, so for the previous project, for the Dobby project, we actually took a robot into 10 different homes in New York and we tried out around 109 different tasks. right? And overall, we had kind of like an 80% success rate, but there were a few tasks where it was like very close to 0. And there was also a few tasks that was like very close to 100. So we got a pretty good sense of like, what are the tasks where it just doesn't work out? So for example, we didn't try, like here, I can give you a very simple example. For door and drawer opening, we really say that like it only works with doors and drawers with handles. We don't try doors and drawers with knobs. And that is because we know that our gripper actually cannot handle doorknobs. So that's, for example, like a pretty clean limitation that I can see right from here.
I'm curious, when the model see a drawer that it doesn't recognize is the usual drawer it's seen before, what does a robot do? It just throws it. It doesn't do anything. Would it try to do something?
That's a very good question. I mean, we've seen many different types of behaviors, right? So for example, and I can show you, right, like different kind of behavior. So here, for example, right? So here's a new drawer. Okay, let's move this video for a couple of seconds. So here's a new drawer, right? And the robot attempted it. What it did was it went right in between two drawers and it didn't work out. However, this is a drawer that it can open if it tries. So what we did was we added some level of retrying on top of our policy that we had. And because our policy was stochastic, if you try a couple of times, the robot generally tend to succeed on those environments. But yeah, I think this is a very good question of like, if you run it in an environment where it just has no idea what is going on, what would happen? And I think there the behavior would be generally pretty random. Yes.
How do you decide when to retry?
So here on this one, we actually made some API calls to LLM or like a VLLM. And the model we're using here was GPT-4o, but I think now there are much better models that we can use to like do this retrying. So we give it a sequence of images, as you can see, from the robot's head camera. And once those images go to the API, we ask the large language model, like, hey, did we succeed in the task or not? And based on whether the model says it succeeded or not, we reset to the base position. And once we reset to the base position, we just roll out the policy from there again.
So how would you do this
sorry, Chris.
What if it's a task where just resetting the base doesn't help? Like the can you're trying to flip falls onto the floor. I guess that's just out of scope.
Yeah. Yeah. So this is actually, I think, a very good way of thinking about it, right? Like there is always this kind of limitation when you're trying to do real robots, right? That your robot could mess up in a way that you really cannot recover from. And so we all, of course, always had like humans on the side kind of like observing the robot. And that's why we say that like without the retrying, our base policies themselves get right around like 75% of success. However, when you do get to retry it, the success rate goes up to 90%. Right? There is that 10% of the cases where one of the two things happen. One is that the environment gets messed up in a way that the robot cannot reset itself and reset the environment. Or the LM basically gets confused and hallucinates the success when there's no success. So
that's fascinating.
Those are the two failure cases. Those are where the other 10% is going right now.
So that's fascinating. So the VLM that's supposed to help you to be a good judge itself is confused. So the judge himself is like the referee who doesn't like forget what are the rules of the game and tell you it's done when it's not done, right? So false positive, that kind of thing, right? Thinking that it's succeeded when it has not. Okay.
Yeah, and I kind of want to show you a very simple example of when that happens. So here is a door in our lab. So here's the door in our lab, right? Like, do you see the trash doors? One of our primary failure cases for the VLM judge happened on these doors because our prompt was asking, is the door open? And because there's this little hole, it assumes that the doors are open. So even if you don't open the door, it just says that, yes, the doors are open. That's one of the very clear cases of like how our VLM judge failed in practice.
Yeah, but I mean, like you said, that
as the
they are
models get better.
Yeah, exactly. As this get better, are you expecting a path that will quickly this case failure might rarely happen? You think it's just something fundamental?
I think we think that this is a very easy problem to judge, right? Like either door is open or it's not open. There's not really that much complication in judging it. I think the requirement that we have right now is that it needs to work for a lot of different kinds of door, right? So here's the cabinet door, but also we've tried out on like different wooden cabinets. We've tried it on metal cabinets, right? Like, we just need a model that works well uniformly on all the kind of different doors that we're trying it on. But I don't think this is a very hard problem. I think once we have a good action model, the verification problem should be significantly easier.
Yeah, maybe this is a good time to dive into the paper in a bit more detail. I know, for example, like I think earlier on you were mentioning the specific way of collecting these demonstrations. I find it fascinating that you just have a $25 thing, right? And then you just put an
$25
iPhone
thing plus an iPhone, right? Like you kind of, So we generally don't talk about the iPhone price because the iPhone, we assume pretty much everyone has it, which is a reasonable assumption to make in the US. But other than that, our tool is pretty cheap.
Yeah, could you say more about like the design decisions around it? I mean, I've seen the other paper like UMI, but I think these are what I call the simpler class where you don't actually involve like teleoperation with actual robots. You just take something that it can quite easily. It's like a thing that a human can just easily like. Could you describe about some of the design decisions? What are the pros and cons using a method like this for so-called demonstration collection?
Give me 1 second. Let me actually pull up the earlier designs so that I can talk about what did we change. Because I think we've been working on this line of work for a while now. And I think it's a good way to kind of like contrast like what has existed. And I'm glad that you mentioned UMI as well, because that is a question that we get very frequently. Like what is the similarity and dissimilarity between us and like the UMI tool? So let me actually go back a little bit further than what you asked and go back into the Bring Robots Home paper. This is the Dobby paper. And this is kind of our first version of this tool. We call it the stick lovingly because the way we built it the first time around is we took a tool for trash pickup. Like you've seen these reacher grabber tools for trash pickup. We took that and then we 3D printed some pieces. And then we added an iPhone on top of it. But the high-level reasoning behind why we went with the trash pickup tool is that because the end effector of the tool was pretty much the same end effector that was used in the Hello Robot. So if you see the images side by side, you see how the gripper end effector is pretty much the same as the robot end effector. And so from the perspective of the phone, from the perspective of the camera, it was pretty much the same. So that was, I think, one of our earlier insights on when you have the same end effector, from the perspective of the camera, from the perspective of the wrist camera, it is very easy for us to transfer the data from the data collection tool to the robot. And that, I think, really lets us scale up our data sets in the wild without having to carry our robot everywhere. So that was the first insight, and that is really what we wanted to capitalize on. Once we had that insight, I think the second question that we try to resolve is how do we make this process easier? If you, for example, go to the UMI website, you'll, for example, see some demo videos of how to collect the data. And one of the things that they really say is that the data that is collected with the UMI tool, that has to be calibrated. And what the calibration means is that there is IMU inside of the GoPro. They use a GoPro tool. You have to calibrate the GoPro. And then what they do is they use some sort of structure from motion algorithm to figure out how the tool has moved over time. And then once you have the data, then you take it back, then you process it, and that is the robot's action. What we went with instead was to use the iPhone. And why did we use the iPhone? Because iPhone has a lot of these APIs built in. The iPhone currently gives you access to the ARKit API, which lets you basically infer the motion of the phone directly from just the phone itself without having to do any post-processing yourself. So you do the recording, and once you're done, the data is already there. And it also does sensor fusion out of the box. So you don't have to do any like fancy post-processing. You don't have to worry about, for example, if you go really up close to a door and there are no visual features, structure from motion algorithms generally tend to fail there. But iPhone works perfectly fine. And that is because it is actually doing sensor fusion from all the high-level sensor and the low-level sensors in the phone itself. So that's another advantage that we had, that we didn't have to do any form of calibration. So once we have this tool, we can, for example, take it into Home Depot and then collect a lot of data in Home Depot from like different kind of cabinets. And that's one of the advantages that we had. We didn't have to move somewhere, do a camera calibration, which takes about a minute, maybe, and then go from there and start collecting data. We could just go, plug in our phone, start collecting data directly.
Yeah.
Once we have this tool,
Mahi, just to be clear, so the iPhone gives you obviously the RGB video, But it sounds like through this AR kit, it also gives you, am I right to say that it's literally a 3D path of where it thinks it's been to, because
it gives you
everything
full
in
3D motion of the phone. Yes. So it gives you the pose and the position of the phone over time. And I think it is able to give it to you at 100.
I see. And,
yes. And it's incredibly
in general
precise.
Have you seen that but I suppose these things do shift over time, or you think that it's at least given the
so
time
iPhone
horizon
actually
of the
does
task
pretty
that
good in like loop closure and stuff. So it is also taking in the RGB information in account. So for example, we've done experiments where we like start recording an iPhone, take a walk around our lab, come back to the same position, see if the loop closed. And generally they do loop closure pretty well.
It's amazing.
Yeah. And again, I mean, this is one of the biggest blessings I would say, because, like Apple is a pretty amazing company and they have a lot more budget than like a lot of our robotics efforts that we have.
Yeah.
So, if something is there, I say we should take advantage of it. And that's my personal philosophy.
Got it. Interesting.
It makes it much easier for everybody to get started too. It's nice to not have to run some custom.
Yeah, it's much more economic.
Yourself. Yeah, probably more reliable. Honestly, like iPhones are used everywhere all day. Yeah. Hundreds of millions.
It's really nice as well. So I mean, I'll plug this a little bit, but our lab recently open sourced an application just for this data collection purposes. So if you have other sensors, for example, let's say you have a contact mic, or you have a tactile sensor that is streaming data over Bluetooth, our lab released an app called AnySense, where you can just download the app, put it on your iPhone, and this will record all of the data together, right, and export a single file. And then you can just upload that file on wherever we use Google Drive and start training policies from that, right? So we're trying to streamline the whole process rather than like, then you have to collect the data, then you have to process the data. Sometimes the data is bad, so you have to filter it out. Right, we're trying to make it much more streamlined. That's the goal that we're going with right now with this.
What is the lowest version of the iPhone? Like how far back have you guys tried? Like
the lowest we've tried out is I think 12 Pro, and we use Pro because the iPhone Pros also give you a lighter depth from the back camera. So for example, my iPhone has a LiDAR in the back. I don't know if you can see it right here. So you can use a LiDAR to collect depth data as well. And that's an extra modality if you want to use that. We haven't used it with a non-Pro version, so I cannot tell you if it actually works as well as the Pro versions. But we have used all the way down from like iPhone 12 Pro onwards, and this feature is there.
Yeah. So in that case, though, when you actually take the data from them, do you take the depth information, or you take just the concluded, like, the final pose, like that the IR kit gives to you? Presumably, they use depth as part of the sensor fusion thing.
I think they're doing internal like sensor fusion with all the sensors that they have.
Yeah.
But our policy for robot utility models is pretty straightforward. Like image goes in, and actions come out.
Got it. I see.
So it's pretty much an end-to-end policy. It runs at 3.75 hertz. Yeah, image in, actions out. And by action, when I say action, it's just really 6D pose and position of the end effector and one dimension of the gripper. That's what we say.
Yeah.
So I was just saying that, like, when the UMI came out, that would be like, I think February of 24. And then we took inspiration from them as well to make our tool a lot more compact. And that's what you see here. The previous version that we had, that was kind of like a long stick. And we made it handheld. We got a lot of help from the people at Hello Robot as well in designing this tool. This time we could make it completely easy to carry. Now you could just carry it back in around your backpack, put your phone in wherever you go, and start collecting data. That's kind of where we ended up in.
Well, what do you think of this? Like this approach just seems so much simpler without the actual physical robot being involved, right? But why do you think there's still, like, I don't know, at least for me, I still see a lot of like research that is sticking to the like follower leader kind of it seems like a super overkill. Everyone can just stick an iPhone and do what you do. Like, where do you think is a trade-off, or is there any trade-off in your view?
I mean, I think there are like a few trade-offs that I can totally easily think of. I think the first trade-off that I think of is that when you have just a wrist camera, you sometimes miss out on the global information. Because if you're focusing exactly where your wrist is looking versus our head camera, our eyes have a lot more global information about everything. And that is something that we really have to figure out how to get from this kind of setup. people have tried, for example, like setting up a camera in their chest and trying different things. I think the jury is still out on exactly how to do that. But I think there is definitely progress that needs to be made to give it a lot more context, right? And I think this is again a problem that will come back to us in like next couple of years, because again, for example, let's say the Aloha setup. It's a pretty good setup for problems that are kind of like tabletop, let's say, right? You have two arms, you have follower leader, you have your workspace is limited within a table, and you can actually solve a lot of problems that way, right? So I think that is by itself like a pretty exciting setup. However, I'm personally interested more in, let's say, a robot that is trying to solve problems in the scale of a house. There you can't really instrument cameras everywhere. There you really have to assume that all the cameras for the robot is on the robot, right? And how do you solve problems in that way? So the problem of context and how do you give your robot enough context to solve the problem is still pretty open, especially when you think about scaling up the problems. And that is something that I think we all need to focus on in the near future. I think we've made a lot of progress in solving problems that are kind of limited in the workspace, but not when the world is open and we can move around in it.
Yeah. Sorry to kind of interject.
I know.
You want to continue sharing?
I was just going to say, I personally very strongly believe that if you really want to get a lot of diverse data, and if you really want to go out there in the real world, right, and get robot policies that work out there in the real world, I think it is very important to kind of relax the assumptions that we make today, right? And the assumptions that we're making today is kind of like, oh, we have well-calibrated cameras set up on exactly the right spot every time. And all of our arms are well-calibrated. And, like the world, like my infrastructure is fixed, different objects just appear on my desk, which I think works for a certain kind of problems, but I really want to get beyond those set of assumptions. And I really want to get to robots that you can just take anywhere, just drop it there and get it to work. That's my hope.
Yeah, I mean, the way you're describing, especially like the way iPhone has such great, like, out of the box from AR kit, presumably even beyond like manipulation tasks at a fixed spot. But if you're just literally going from one bedroom to the bathroom to do something like that involves navigation, I suppose iPhone can easily give you that, right? I mean, over that kind of range, it's still.
Chris and I have like worked together in a few projects, and like in most of those as well, like we've used iPhone as like almost as a ground truth, right?
Awesome.
Because the data that we get from the iPhone is so good that we can use that as a ground truth, and we can figure out like not exactly how, but exactly where a lot of things are, because you can get the full trajectory of the phone. You can get the depth information, which is also very robust, especially when we're comparing against the baselines of, let's say, Intel RealSense cameras. So we can really use a lot of the iPhone information as a ground truth information and use that, for example, for navigation, use that for mobile manipulation. And I would definitely say that that's one of the things I'm surprised roboticists are not using more, because it is such a out-of-the-box solution for a lot of problems.
Would have guessed, man. Apple is I mean, another reason to buy iPhone.
They're positioned really well to just, do a lot of the problems out of the box. I agree. Sorry, I was just going to add like one thing on top of what we were just talking, because I think this is also something that is very important I want to talk about. It's kind of following up on like what you just said, right? About the pros and cons of, let's say, this kind of like handheld robot-free setups. And this is something that I personally found very exciting and also very enlightening. So let me pull that up very quickly. There are two plots that I kind of want to show in the paper. And here are the two plots, figure 10. But let's just focus first on the left plot. And the left plot is something that I really, really appreciate, like learning from the effort that we took, because it's talking about what kind of data sets you may need for generalization in the real world. And let me explain this a little bit more. So the idea, of course, like what we want is that you take your robot, you take your policy somewhere new, and you get it to do the work that you want it to do, right? And a lot of work that we're seeing today, they'll talk a lot about the architecture, they'll talk a lot about the algorithms, but they won't talk really a lot about the data itself, right? What is the data that was trained on, and how does the data contribute towards, let's say, the generalization that you see from the model? And we wanted to understand that. So what we did was we did some experiments of this sort where you can see the two shades of the bar. One is diverse data and one is uniform data. The difference between them is that they're both data sets with 1,000 demonstrations each. However, the one on the left, the diverse data, that has 40 different environments. And the one on the right, the uniform data, that has 5 different environments. And when you train models on data that is collected from 5 and 40 different environments, some of the tasks, you actually see a big difference. Here we see a big difference in object reorientation because once again, the objects that we're trying to straighten on the tables, those objects vary a lot. They vary in size, shape, color. They vary in weight. The physics is different. The visuals are different. And what we see is that having the diversity in the data is actually crucial. Even if you have the same number of demonstrations, just having less diversity in the environments reduces the performance by about 50% in the tasks that we have. And that's one of the reasons why I also believe in this kind of handheld setups, because you can really easily get a lot of environment diversity than you can get in, for example, some sort of tabletop setup. Or, for example, where you have to carry your entire robot into a new environment, get data with that. So I think there is definitely certain promises that I would like to see come to fruition by following this direction.
Yeah, I'm curious what you think. So it seems like the difference between the two is about one order of magnitude, let's say eight times the difference in terms of number of environments, right?
Yes. Let's
say if you were to do another 1 or 2 orders of magnitude, which just seems super doable, it's like, so jumping to 40, so 5 environment to 40, and then now maybe 40 to 400, let's say, environments. Are you expecting, like, what kind of improvement are you expecting? Or have you even tried?
Yeah, I mean, I think that's a very good question. Let me go back to the plot again, right, and talk about it a little bit more. So on the left one, right, like you kind of see like the door opening, and the door opening there, it doesn't quite matter as much as it matters in object reorientation. And that, my personal hypothesis, is because there is much less variation in door physics than there are in, let's say, random object physics. And I think that is where a lot of those critical choices will come down to play. And so what you'll see is for somewhat reasonable but somewhat simpler tasks, you'll probably not get much of a benefit from going from 40 environments to 400 environments. But if you think about tasks where there are a lot of variety and a lot of uniqueness, something that is different everywhere, I think there you can see a lot more benefit from going from 40 to 400. However, this is something that I definitely think really merits more examination and more experiments because, like right now we live in a very different era of robot learning where like something that works from 75 to 90% is probably good enough for us in academia. But if you want to put this into a product, if you want to get this to work reliably, then you'll start thinking about, like the number of nines. And that is also an open question of like, how do you get something working from 90% to 99% or 99.99%? And I would definitely say these are open questions. I really hope that people are trying to answer those questions. Like hard to do that in the scale of academia, but I'm hoping that other people will pick up this thread, really scale it up to, let's say, 400 environments and try to see what happens then.
Yeah, exactly.
I really like what this paper has to... Yeah.
Like Chris?
Oh, I was just saying, I really like what this paper tells us about generalization and how to get generally useful robot models. I think it's definitely interesting to think about. So just to go a little bit further on what you were just saying, Mahi, what do you think that this is a bad sign for like just like the ARM farm tabletop data collection kind of things? Do you think that'll be, do you think that will result in generally useful like pre-trained networks like what you're building off of, or no?
I think, okay, so this is something that I've been talking about every time I talk to people about these things. And I personally believe in our robot future, there will be as many different types of robots as you'll see dog breeds today, right? And I generally think that different robots, different embodiments have their places in very different places of society. And I think ARM farms have their place. And I think, somewhat weak mobile robots have their own place. And I don't think there is like the view of one versus the other really makes much sense to me. I'm personally very interested in robots that are mobile, robots that are able to do certain things in human environments, and ideally robots that, if they malfunction, they can't do much harm. Right. I think those are the ways I think about it. But for example, when I see what Chris was talking right before we started, like the Gemini robotics work on the Aloha platforms, right? I think they also have their own place. And I think they also have their own focus on if you restrict the robot on this certain like tabletop setup, what is the performance that it can get out of it? We all have to make assumptions, and I think different type of assumption make for different kind of work and different kind of robots. I do personally believe that like if your goal is to really like take a robot out there in the world, then I think we need to figure out how to disentangle our robots and our data for our robots from just tabletop scenes. But that doesn't mean that like the tabletop scenes themselves are not making interesting progress in the world. Does that make sense?
Yeah, I think that's fair.
Yeah, but I definitely do think, and I definitely do want to invite more people to really kind of look closely at the training data sets that they're using, right? And try to get a good sense of like what is in the training data, what is not in the training data, what's the generalization that we're seeing, and what is, let's say, a nearest neighbor kind of interpolation that we're seeing, right? And that will be very useful for us to also get a good sense of like, at which scale of data will we see this type of generalization falling out? And I will say very much kind of like an anecdotal experience, because when we were going about it, when we were thinking like, hey, we want to train a model that can open doors, right, in new environments, we weren't really expecting it to work with just 40 different environments, right? We went there, we trained a model, and we were like, wow, okay, this model's already showing signs of life. Great. And that was, I think, at 20 different environments. And so we scaled it up a little bit more, and it was working decently well. So I think there is a lot of surprises waiting for us if we make the right assumptions, if we explore it. But right now, I would definitely say that not enough people are really looking at it. There was another paper from Xinhua, I think. That was the data scaling laws, came out, I think, right about a month after us. And they were also looking really closely at very similar setup, handheld tool, and like 4 different tasks, I'd like to say. And they were kind of like figuring out like how many demonstrations do you need? How many environments do you need? And they ended up at a very similar conclusion to ours. There were like 1,600 demonstrations. I think 32 different environments is what they were suggesting. Like I feel like there is some underlying truth to it that we're approaching. And I would really like to have more people looking at it more closely and think about how exactly we arrive at the truth.
Yeah, could you also comment a little bit? I know that in the paper you tried different a couple of different like policy architectures.
Yes.
Is there any like significant difference, or you think that, I know in the paper you kind of suggested that maybe data diversity matters a fair bit more than the policy architecture?
Yes.
And you have a couple of charts you want to kind of walk through a bit?
Yeah. Right. There you go. Here are the plots that I'm talking about. And what we've seen here, right, just to give a little bit of introduction. So the diffusion policy, I think people already probably know about it, but this is, like the standard diffusion policy algorithm from then Columbia, now Stanford lab of Shuren Song and her students. Then the VQBET is a vector quantized behavior transformer. That's the algorithm that we developed in our lab. But the end goal of the both algorithms are pretty similar in the sense that we both want to learn from multimodal data that has multiple modes, multiple ways of solving the same problem, multiple correct answers. And when we compare it head to head, what you see is that really the error bars are overlapping for almost all of the experiments that we have. Even though the mean performance of VQBET seems a little higher, I would say that is probably because we created the VQBET algorithm and we have a better way. We just have better know-how of how to tune the algorithm, right? So maybe it was done by someone else. Maybe if it were done at Stanford, maybe they would have gotten better performance out of diffusion policy. But the more surprising part is when we tried even lower capacity algorithms. So here on the bottom plot, we tried ACT and MLPBC. So ACT is action chunking transformer. MLPBC is really a resonant and 2 layers of fully connected neural network. And even there, right, the performance drops off, but it doesn't drop off too far away. And that really, what it tells me is that while we have really focused a lot on finding the right algorithm for imitation learning and behavioral cloning, what might be more important today is really focusing on what data you're training your policies on, rather than trying to micro-optimize what exactly is the algorithm that you're training it with. And I know that there is generally kind of this perspective where one of the research seems a little bit more glamorous than the others, right? No one wants to just sit there and do data curation. I understand that. However, I think there is a lot more alpha to be found by really looking at what is the data that you're training on, what's in distribution, what is not in distribution, and how do you get the most out of it, rather than trying to spend another 6 months a year trying to micro-optimize whatever algorithm that you're training on. And this is actually one of the fun parts of this research as well, because when we were doing the evaluations, that was one of our bigger bottlenecks. Because we're doing our evaluations in the real world, we have a set of 5 different environments that we ordered off of Amazon. And so every time we want to evaluate a policy, it's 5 environments times 10 trials. So that's 50 trials in the real world. You move around the robot, you put it into different places and you run it. So that really bottlenecked how much fine-tuning or metric hacking we could do. And I think with limitations like that, we'll make a lot more real-world progress, I would say, in trying to figure out what really works and what doesn't work.
So just to clarify, you're talking about like after you train the model, but to evaluate the model, like the success rate and all that, like the real world difficulty of actually collecting evaluation in the real world. I see, got it.
Because someone has to babysit the robot and someone has to watch it run, and someone will have to stop it from doing really stupid things.
Got it. Could you talk a little bit about the whole like training? You did this like three or four different policy architectures. Like what kind of compute is needed at the scale of data that you guys are working at, say 1,000 demonstration roughly?
So this is actually one of the fun parts of the research. I know that, there are a lot of interest in like really big models these days. But for our tasks, our models were pretty simple, pretty small, and we could totally train them on, let's say, desktop GPUs with 4 A6000s, or 3 A6000s, 4 A4000s, or for example, when we're training it on the NYU cluster, we're training it on, let's say, 2 A100s for like a day and a half, something like that. So the iteration speed was really much faster, and we really didn't have to do, let's say, the large language model thing where we just let a model bake for 1 month and then whatever comes out at the end is what we get. We could iterate, we could move really fast. And because our models are really small as well, we could really run it on the robot. The videos that I showed you on the Hello Robot Stretch, the Hello Robot Stretch has like a NUC with what's the processor? I think Intel Core i3 to Core i5. And we were running our policies at 30 FPS on that NUC itself without a GPU because our models were just that small.
Interesting. So that's at inference after that's actually deploying the actual policy.
Yeah. And I think that's kind of our goal as well, because we're taking our robots into different places. We even took our robots to Coral at Germany, and we were doing demos there. And the conference Wi-Fi, if you're familiar with it, it's always terrible. So just having something that can run locally on the robot is just such a godsend that we just stick with that now.
Got it. But I mean, I imagine, let's say, you mentioned about like the data diversity and also the scale of data. So let's say if you got your wish, someone helped you 1,000x amount of data, then presumably, am I right to say that the compute needed to say train the model in the first place is going to like also, you mentioned you need a couple of like GPUs, like kind of consumer grade, but if you have 1,000, does it mean you nearly need 1,000x if you want to train roughly around the same, like couple of days? Is that how?
I mean, I think that's a very good question, right? So I'll say that right now when we're training it for 500 epochs on our 1,000 demonstrations, right? So 500 times 1,000, 500,000 episodes it has seen. If you really give it, like 100x the data, I don't know, like it might have a good performance after training for 5 epochs. We know that, for example, LLMs are trained for like 1 epoch, sometimes less than that. I am not really certain that we'll still have to be training for 100 times the more time. It just might be that because you're training on such diverse, rich data, high quality data, it might just still take less time than whatever we're expecting right now, but just be a stronger model because it has seen more diverse environments.
So more data, but just less epochs. And so therefore the compute budget could be similar.
Yeah. So the way I think about it, right, is that really when I convert this data to a video and when I save it to disk, it turns out to be somewhere around 1 gigabyte. And if you think about like 1 gigabyte, it is not that much of data. And again, you think about it really like we're not even trying to like learn how to generate these videos. We're really learning how to act based on those videos. So the models that we put out are at the end of the day somewhere around 80 megabytes. And so when I think about like what is the best parameter set of like 80 megabytes that we can learn from the data, it doesn't really seem to me that you may need that level of compute to get there. And it might be different. It might be that like, if you really want to get 99.999% of accuracy or success rate, you may want to do something differently, right? But it doesn't make too much sense to me that like that is probably the right way to go. I personally believe that like if you're really like desiring that level of accuracy, maybe you're better off just like trying to fine tune a little bit in the real world with some type of reinforcement learning. Because if you have a model that works, let's say 99% of the time, it should be very easy for you to just roll it out a few times and see what works, right? So that's, I think, probably a more promising route than really trying to see, okay, what is the X of the data and how big of a model can we train on that? But again, like all the comments I'm making are limited to our experience of like training single task models. These are the utility model. So if you really want to go and train a very large model for 100 different tasks, that might have an entirely different set of lessons than what we have here and what we're preaching for. I think for us, what really matters is really getting something to work, right? I think for us, like really like the fanciness of the algorithm and the fanciness of like, I don't know. I think I'm personally more interested in training something that works than that works out there in the world.
I'm also curious about, like, you mentioned somewhere in the paper about the difference between expert and non-expert. It seems like it makes a fair bit of difference. Could you like share that chart and go through some of the learnings?
Absolutely. I think that's one of the biggest and more interesting lessons that we've learned. So this is a lesson that we learned on our previous project, the Dobby project, right? Where we're giving a tool to people and we're getting them to collect 5 minutes of data, and then we're fine-tuning for 15 minutes. This is a lesson that we learned there. And the lesson was that when people were collecting data, the first time they collected data for any task, doesn't matter what task it is, and when they rolled it out on the robot, the policy that they trained, it was uniformly bad. It was uniformly bad. It would maybe get like 10% success, maybe less. Okay. However, the way to mitigate this trouble is to literally collect data and then show them how the robot is acting when policy trained on the data is running on the robot.
Show them, meaning the humans.
Once you show them that, yeah, and then you have them collect data again, they are much better at that. And I think my personal hypothesis, again, we haven't validated it experimentally, so I'm not gonna, swear by it, but I'll definitely say that it seems like people need to learn how to think like robots especially when they're trying to deal with this kind of limited, a lot more, let's say, lower cost hardware. And again, we were running all of our experiments, or most of our experiments on the Hello Robot stretch. So there is some component for people to learn how to act like a robot. And that's what we call like experts here, right? The experts are really people who have learned how to act like a robot. And the non-expert that we talk about are people who have not learned how to act like a robot. So let me share the screen and then let me tell you what the result we get out of this. So when you have expert and non-expert data, here you go. When you have expert and non-expert data, as you may expect, expert data is just better than non-expert data, all right? There's no questions about it. You can always, if someone's an expert, they're going to collect better data. And again, what we're doing here is imitation learning. The robot is trying to learn how to imitate. So of course, if we mix in non-expert data, it also imitates the non-expert data. So the performance is lower. However, what we did find out, and what was really interesting for us, is this plot on the right. So what's happened on the plot on the right, as you can see here, is that when you mix in for drawer opening, the expert and the non-expert data, right? So here's 500 demos, 1,000 demos total, right? 500, 1,000. When you mix in the non-expert data for drawer opening, the performance actually goes down from the expert to the mixed data. And why is that? Again, I think the intuition is very simple. If you're training with the multimodal policy to imitate a mixed quality of data, then the policy you're going to get is also probably going to be of mixed quality. And that is really what we observed here. And that was kind of against the popular intuition of that you should be trying to train your policy on as large of a data set as you can. What we were saying is that maybe for some tasks, you'll actually get a benefit if you curate your data set and throw out some of the bad demonstrations rather than trying to maximize the size of your data set and train on as large of a data set as you can. So that's one of the pieces that I found very interesting and some lesson that I learned that I try to follow.
Yeah, but it seems that on the door opening, the co-training is better, right?
Yeah.
76%.
Yeah. I mean, again,
yeah.
I think
Interesting.
I think the way I think about it, right, is that when we're labeling data as expert or non-expert, this is also a very noisy label. And there is not a very good way of saying that, like, this data is of 95% quality versus this data of 60% quality. This is a very coarse label. And while it may help, it may also hurt. And really the lesson here is that you should be aware of the data mixture that you're training your policies on, rather than prescriptively saying that A is always better than B.
do you think that data, that worse, lower quality data, still has utility for things like pre-training your image model, or like what if you conditioned on the expert level when you're training the policy, things like, or do you think it's just a net negative?
I totally think that there is, like I think some people always, not always, but sometimes talk about the data pyramid, right? Like the data diet of robots, right? Like there is a lot of like out of domain data and you get a lot of benefit from like pre-training on it. And we've experienced the same thing. So for example, when I was talking about the previous project, right, the Dobby project, where we're like, oh, you have a pre-trained model, you fine-tune it for 15 minutes on 5 minutes of data, right? The pre-trained model is actually a ResNet that was fine-tuned with some self-supervised learning algorithm, MoCo v3, on a data set that was collected by non-experts, right? So that was about a 13-hour data set of just play data. And we saw that like training a policy on that play data actually hurts a lot. However, if you train a visual representation on that data, that really lets you hone down on what is important, and then you can fine-tune that model for like 15 minutes to get a new policy.
So you did train that on just the expert data and it was worse than training it on everything? Or
sorry, the visual head?
Yeah, just the visual head. I'm curious.
So we have never actually tried that, where the visual head we take like a raw ResNet, because we were using the same representation for a lot of different tasks.
Yeah, makes sense.
It could work, but what we have found is when you have a very little amount of data, and especially when you have a very little amount of visual data, it might help a lot to even have like the same in-domain visual pre-training. And again, this may be like slightly different result than like, because for example, there are a lot of example works that people have tried where, they train on some level of like off-domain data, right? Like something like Epic Kitchen or something. And we found that like it helps much more if you pre-train on that in-domain data, even if it's slightly out of domain. Even if it's not showing expert behavior, it is showing you household behavior. It is showing you a lot of household data. And from the same form factor, right? It is coming from the same wrist camera, same iPhone, whatnot. So that helps a lot.
Except, cool. Yeah, it does seem like, I thought this was really interesting work. Really cool to see, like, especially to see robots and generally generating models that you can actually like download and try is something that I feel like it's understated how little that happens in robotics. So it's very cool to see. And like I said at the beginning, like I did actually try these models out in my house and they worked. I was able to open a drawer. Yeah. So, and things up right, all that kind of stuff.
Doing more demos. Yeah, hopefully we'll be doing more demos. We'll be bringing our robots to the conferences. We've already done demos at Coral. Last year.
We were all at Coral. Yeah. We were.
So Coral demos were really fun. I couldn't be there personally myself, but my undergraduate student, Hariteja, who was also my co-lead on the project, he got a robot in Germany. He went out and got a cabinet from IKEA the day before. And this was a cabinet that was totally not in our data set. It had kind of like a transparent shelf front. So he just put it together and then we did demos for the whole day, opening doors, opening drawers. And then the next day we unpacked it, tried to return it to IKEA. I don't know if he actually returned it or did we have to like give it away. But that's the kind of demos that we're doing. Hopefully we get to do more demos of that sort and hopefully people get to experience it for themselves.
And does that live demo also like have that judge thing that you call to GPT-4o? Does it have the retry thing as well? Okay.
It actually depends on how good the Wi-Fi is at the conference.
Yeah, I was going to ask because you said the Wi-Fi wasn't great.
Yeah. So if the Wi-Fi is bad, it just times out, and the retrying thing, the human has to judge and be like, okay, retry now.
Got it.
So that's a harder part to demo, but hopefully as, like local models are getting better. I mean, like Gemma 3 came out yesterday and it seems like a pretty good model. So maybe we can try out something locally and get the verification part working locally as well. I think that'd be exciting.
Yeah. I remember seeing something in your paper where you say when you get GPT-4o to decide and when you retry, you average out something like 1.3 tries and manage to get it or something like that, is it? So
yeah. I mean, I think
that is from 70-something% to 90%. So that's a pretty significant jump once you are able to do this retrying thing.
Yeah. I mean, I think, so let me just share my screen for one more second and I think I can show you pretty clearly what I'm talking about here. So this is really what we're talking about when we're talking about like introspection and retrying. And you're talking about the middle plot, like mean tries to success. The way we define this is really how many tries you have to try it, how many times you have to try it before you get a success on the policy. And again, sometimes you just don't get a success, sometimes it fails completely, right? Or like it creates an environment where it just doesn't work. or, like it cannot reset itself. So excluding all of those, when it does work, we wanted to see how many times you have to retry it. And it turns out it's right around 1.31, which makes a lot of sense because, if you have something that works 75% of the time, in expectation, you have to try it around 1.33 times before you get a success. So, like the number pretty much checked out. And we're also pretty happy to see that this retrying thing actually does work reasonably well. Again, it's working because the policies that we have are multimodal, right? So when you start the policy from exactly the same position, when you roll it out multiple times, you do get different results. You do get different kind of behavior. Sometimes when it's trying to open a door, sometimes the robot will rotate its wrist left, and sometimes it would rotate its wrist right. And that's kind of like what really comes down here. And on the right plot, you can also see like the false positive rate that comes from our model, right? Like our vision language model. And that's hopefully something that will also get better over time.
False positive. False positive meaning it thinks that it was a success when it in fact failed. And
yes.
So it didn't even bother to retry.
Yeah, it's like, I've succeeded. All right, done, stop.
Okay,
so
got it.
That's one of the things. So for example, one of the Bago pickup thing was actually a pretty surprising failure for us. But it turns out that when you're looking through the head camera and you're looking down at the wrist, like sometimes it's hard to tell if you like actually picked it up off the surface or not. It looks pretty much the same. So, I think better sensor setups, better camera setups as well. I think all of those things will contribute to having fewer false positives.
Yeah, also, I mean, this was GPT-4o, right? Like, it's a pretty old model at this point.
Yeah, this is like, we made a lot of advances in the time since the paper was written. So if we try it now, it might be very different.
Be very curious to see how well it improved on that, like, retrying benchmark of,
yeah. I think it'll be really fun to try. The models are out there, so, you can just download and try it.
Yeah, absolutely. And as you're saying, there's many more cool open source versions that you can run locally. So those are also always getting better.
Yeah. And then that's kind of like the hope at the end of the day, right? Like, I personally really believe in having like local models, right? People can just download, people can run, have full control over it. I personally think that that's probably the way I'd like things to go, especially for robotics. The locality matters a lot. And right, like I, for example, don't want to like record my home and like send it over the internet to some server that I don't control. So that's something that I personally care about.
So I guess, to wrap up on the paper, what are some of the future directions that your group is trying to take? Like what would be the natural next few steps?
I personally really believe in the direction of just having generalizable utility models. I think that having this kind of like atomic structure, atomic tasks that the robot is able to accomplish, will really open the door towards kind of like higher level of cognition, right? Like I think we have this sort of like Moravec's paradox going on where a lot of like high level planning and solving IMO problems are much easier for AI to do than to even like go wash my cup in the sink. And really, I think that like having this kind of like generalizable primitives, generalizable modules, units would go a long way to kind of solve this kind of problems where we can attach together different Lego blocks and we can get it to work. So one of the primary things I'm personally interested in is really like figuring out this whole setup where you can just take a robot, drop it into a new home and get it to chain together different utility models and do something useful. How do you decompose a high level task? How do you create this scene memory? How does a robot know what's where and where to do what and how to execute, where to execute, what to execute? I think all of those questions are things that I'm interested in and things that I'd like to figure out how to do next. I think there are a lot of like interesting questions that comes to, let's say, the verification piece of the puzzle. Like what is the right way to verify? Here, we're kind of like going through all the way and then we're like stopping and checking. There could be something a little bit more proactive. There could be some sort of like world model as well that is trying to predict forward and saying like, oh, am I in a risky situation? Should I just reset already? Instead of going all the way and then waiting for it to fail. So that's something that I think would be very interesting. And I think one of the bigger pieces of the puzzle is really like figuring out a little bit more dexterity for the robots, because the tool that we have really has like 2 fingers, act almost as a parallel jaw gripper. And there are certain things you can do with it, but there are also certain things you cannot do with it. And so thinking about how do we get this, for example, robot-free robot data collection working on a little bit more dexterous setup, right? That is a big open question. And I think that would be really, really interesting to explore. Like what would be a utility model? What would that look like for a bimanual dexterous hand robot, right?
Wow.
So These are
you
all
need two
open
iPhone
questions.
to begin with.
I'm personally very curious in those, but yeah, like if people want to do research on this, I think these are very valuable questions to do research on.
Yeah. Well, maybe one final question for me. What are some like really cool papers that you read recently? Yeah. Do you think was just mind blown?
That's a very good question. Let me think. Are you asking like specifically in robotics, or are you thinking all of ML, all of like everything?
That's a good question. Back to me. Well, I guess maybe more robotics. I guess as a start, but I'll be curious if there are other domain, maybe in computer vision that you think it's blew away and maybe has opened up some new possibility in robotics.
Yeah, I mean, I think I would personally say that I've been personally following the line of work. Are you familiar with the Duster line of work?
Yep.
Yes.
Yeah.
So multi-view 3D generation. I think following up on that, I think there was one work from Andrew Davidson's lab, Muster Slam, is something that I read recently, and I think so. We tried it out on
real time.
It's almost real time. On my machine, it was not real time, but it was like pretty good. It was, I think, 5 FPS, and it was just doing like 3D reconstruction from a monocular camera, and was also reconstructing the entire like pose graph and like doing full slam on top of it. And the code was beautiful. It was wonderful to read. And I think I've been looking at that line of work. I think there was another work from Berkeley, I think from Anju Kanazawa's lab called Cuter. I think that was kind of like a sequence of images come in and reconstructs an entire 3D scene on top of it. Yeah. But anyway, so I've been looking at that line of work. I think that's one of my personal interests as well, is just really like taking a robot and not restricting it to a tabletop, but really like blowing up the workspace, getting it to work in an entire house, entire home, entire floor of a building, whatnot. And the question is like, what are the new interesting problems that come up when you do that? So that's the line of work that I've been like reading pretty interestedly. And I think there's been going a lot of like new and exciting work going on in that space. So, I think I really appreciated that line of work. And I think a lot of breakthroughs are being made, and I'm excited to see where this goes and how we can use this for our robotics projects.
Cool. Yeah. Maybe we should try to get all of those authors and come on, talk about Duster.
Yeah.
Chris, do you have any more questions?
I think I'm good. Thanks. Yeah. It's always fun to discuss this stuff. It's an exciting direction. Thanks. Yeah.
Yeah. It was really fun talking about this as well. I mean, I always love talking about our works, and like, just to pitch it again, like everything here, what we talked about today is open source. Like the data, the code, even the data processing code, there's a data explorer that we have. You can just go click around, see what data we've trained on. The data collection tool, all the 3D models, everything is open source. So you should just be able to download, build it yourself. If you have an iPhone, go collect data yourself. The app that we use to collect data, that is also open source if you want to build on top of it, right? We really strongly believe in making things open source because we believe that there's only so much that a single lab can do. But a community, now that's something. And so I really would like people to, try to go take a look, explore the code. If you have questions, if you try something, doesn't work, send us an email. We're always happy to help. So that's one of our very driving values in our lab. And I'd really want to reiterate on that. And I'd really want to invite more people to adopt this philosophy of hey, we want to enter this era of reproducible robotics. So let's do the work, even though it's hard, to get to the point where we can just do that, where we can download a model and run.
Awesome. Yeah, and of course we'll drop all the links that you mentioned just now, all the code or open source 3D models and whatnot in the show notes. Anyway, thank you so much, Mahi, for spending the time.
Yeah, thank you so much for organizing this. This was wonderful and lovely to talk with you guys, and really, really appreciated this opportunity.
Cool. All right. Yeah. Okay, Chris. I know you're kind of involved in the paper in the first place, but after this chat, anything that reinforce some of the things that you learn when you guys are working on this paper.
So some of my favorite things about this work, this whole line of work, are that it allows you to it's the testing of robots in the real world, and the fact that you have models that you can just download and try in different locations. I think that there are very few times when you can just one of the cool things for computer vision research, for example, I can download a model an object detector like OWL or YOLO, and I can just I know it'll work, right? That's not something that we ever have with robotics. And for it to really get to the point where it really explodes, I would expect that to work like to actually be true, right? And this is the first time that I feel like I've had that experience where just like, yeah, you just kind of can try it and it runs. And it's not perfect, but it's really cool. And the fact that all this tooling exists and it's open source and it works cross-platform means that I think it's a really interesting starting point. And that's one of the things that we talked about a bunch. We also talk a bunch about sort of scaling for robotics and how like and what the implications are for data diversity and how we can build better models or better. So I think, yeah, it's a lot of interesting work.
Yeah, I think for me, like the biggest thing, actually, biggest takeaway is just that iPhone and AR kit is wonderful. We should, with iPhone 12 Pro, which is a pretty old model, you can get it used really cheaply these days.
Yeah.
It's just, yeah, I kind of agree with what Mahi was saying. Like a lot more researchers should just look into using iPhone as data collection. I think he was trying to being polite when he said like, oh, maybe tabletop has its place. But for me, looking at what he's doing, it's so much like you just free up, throw away all the big like clunky setup. You just let the human put an iPhone, get a gripper, and then start doing stuff right everywhere. Right, it could be outdoor, it could be indoor, right, and so that just opens up so much more, or rather, like really lower the setup, and it's So I think that's definitely something there. Yeah.
Well, there is something to be said for the fact that the models that he's training you said they were 80 megabytes, right? So it's 20 million parameters, right?
Yeah.
So these are tiny models compared to what you're usually using, right? Like compared to the many billions that you see in like an LLM or a robot foundation model, right? So like, I think that these are like real edge deployable kind of things too, which means the data scales so much more comfortable if you want to train one just for yourself, which is also kind of nice.
So it seems to me like he is taking like the way it may scale for him is to have a lot more of this utility, like small bite-sized modular models that do very, very specific tasks, like opening a door, they're opening a drawer, and then I imagine eventually you put a big VLM that do the the long horizon planning, and then but if you have a plethora of skills, then it can do a lot potentially. And so
very cool.
Yeah. All right, cool, awesome. Let's do this again next week. All right.